All right, so we are talking lesson 5.2, talking about the LSRL. All right, and the LSRL stands for the least squares regression line, the least squares regression line. And what this line is, it's a line of best fit. It's the line that is as close as possible to the points in your scatter plot, okay? All right, so this is kind of what the LSRL in a general form looks like. Hopefully you notice something a little bit interesting, the hat on the Y, okay? So this Y with a hat on it, the hat means predicted Y, predicted Y. And that distinction is pretty important, okay? So B, that's your slope, the number in front of X. And the B represents the predicted amount by which Y increases or decreases when X increases by 1 unit. So hopefully that looks kind of similar to your concept of slope from algebra 1, right? When X increases by 1, the Y will change by whatever value the slope is. All right, A is the y-intercept, and that's the predicted Y value when X is 0. All right, and sometimes the y-intercept might not make a lot of sense in the context. So slope is always pretty important to interpret, but sometimes the y-intercept may or may not be important depending on the situation. Okay. Oh, and I just realized you have some blanks in your notes that I think I skipped over. So the top part where it says, what is the objective of regression analysis? The X variable is the explanatory, or sorry, is the independent or explanatory variable. X variable is the independent or explanatory variable. And the Y value is the dependent or response variable, is the dependent or response variable. And we will use values of X to predict values of Y. And that's what the line of best fit is used for, right? It's used to predict values of Y, which is why we need to have the hat. We need to have the hat on the Y. All right, so the least squares regression line basically is a line that minimizes the sum of the squares of the deviations from the line. Okay, so let's unpack what this actually means. All right, so here's an example, 3 dots, okay? Using your imagination, all right, visualize like a best fit line. Like you can put your arm up, you can like change the slope, you know, but visualize a best fit line, okay? So this was my best guess. All right, I don't know if that was similar to yours or not. This is my best guess. And the deviations from the point to the line are these red values, all right? These are called residuals, residuals. All right, I know I don't have a spot for that in your notes, but we're gonna be talking about these a lot later, so feel free to write it down now if you want. But these, like distance from the line, all right, that is a residual. Positive if it's above the line, negative residuals if it's below the line. And what we're trying to do is we're trying to minimize these spaces, right? These residuals. So we square all of them to make them positive and we add them up. And this is the value I get, 61.25. So what we're trying to do is we're trying to find the line that minimizes that number. Okay, so visualize again where you think the line will be. And this time I will show you the best fit line. Let's see how close your imaginary line is to this one, okay? Ready, set, go. Okay, I don't know if your line matched that line, but I know my line did not. Okay, but this is actually the best fit line. And the residuals, if you were to square them, add them up, 54. right? That number is lower than the previous one. And in fact, there's no line that you can make in these 3 points that would have a lower sum of squares, which means that's why this is the best fit line. Okay, so that's what we're trying to do. That's what we're talking about when we talk about best fit, is to minimize the sum of the squares of these residuals. All right, so that's the concept. That's the idea of this best fit line. So let's try an example, and then we'll play around with how to calculate this line and yeah, how to interpret the slope and the y-intercept and all that. Okay. This is a lot to read, so we're not going to read through all of it. Basically, there was like a study about cancer, and they use mice, all right, to kind of test to see if pomegranate juice helps with tumor growth, all right, or I guess decreases tumor growth. So X is the number of days after the injection, and Y is the average tumor value. Okay, so go ahead and practice right now with your calculators to make a scatter plot. Okay, so practice. And let's see if we get the same scatter plot. By the way, Luca, were you able to fix the calculator issue you had before?
Yeah.
Sweet, okay. All right, and let's see, Margot, whenever you're done, can you just kind of describe what you're seeing once you have your scatter plot?
Okay, I don't know if this is right, but it kind of just looks like pretty much a normal like R equals 1. So I don't know if I.
Yeah, super strong.
Okay.
Does it look like that?
Yeah, yeah.
Perfect. You got it. All right, so hopefully your graph looks like that, and that means you graphed it correctly. Okay, so it's very, very strong. R, it looks like it's going to be really, really close to 1. Good. Okay, so that's our sketch of the scatter plot. And yeah, don't worry about sketching it. If you guys have it on your calculator, you're good. Let's calculate the LSRL now. So with your calculators, let me go ahead and switch this out. All right, so with your calculator, what I want you guys to do is go back to where you found correlation. All right, go back to where you found correlation. So go stat, move to the right to calc, and then pick either number 4 or number 8, either one. All right, either one. I think this time I picked number 8 just to change things up a little bit. So if you want to pick 4, you're fine. But if you want to match mine, pick number 8. All right, and let me just double check. Karis, what are you getting for the y-intercept?
Negative 269.75.
Good, yes. Okay. So if you guys are getting a y-intercept of negative 269.75, you're good. You got it right. Okay. And the slope was 37.25. Now watch, this is how you want to write your equation for the LSRL. Look at this. Notice I don't have y and x. I actually have the words that represent y and x in my equation. Why I like doing this is it gives you automatic context points. All right, you get automatic context points if you do this. So we have volume of the tumor, right? So volume for your y, days for your x, slope is positive 37.25, and y-intercept is negative 269.75. If you guys switch the order of these, I'm totally okay with that. If you do 37.25 times days minus 269.75, perfect, you're good. The thing, listen carefully, the thing that people will usually forget is the hat. Make sure there is a hat over your volume, okay? In fact, I usually make the hat a lot bigger, and I'll draw the hat over the entire thing. All right, but I couldn't figure out how to do that when I was typing. Okay, so just make sure you have that hat. All right.
Wait, is it fine if it, sorry, is it okay if it just goes over the V, or do you want it over the whole word?
Usually I do it over the whole word. Yeah, I just couldn't figure out how to type it in that way.
Thank you.
Right. Yeah, no problem. Any other questions on how to write the LSRL equation? Okay. R, it's in that same list. So you just get an R of 0.998 for this. So yeah, Margot, you were right. This was really, really close to 1. Very, very, very strong. All right. So let's get into this. Interpret the slope. Let's start with that. Interpret the slope. All right. So when you guys interpret the slope, this is generally what you want to say. All right, I'll write it up here. Let me do this in a brighter color. All right. When you interpret the slope, what you basically want to mention is that when the x variable increases by 1, always 1, the slope is how much the y variable changes, right? So I would say the predicted y variable increases or decreases by, and then you put the slope. So I'm going to put in parentheses what you need to like change out depending on the problem. All right. So that's kind of like your general interpretation, right? The slope is when your x variable, whatever it is, increases by 1, the predicted y variable will increase or decrease by the value of that slope. So in this context, I would say when, and my x variable is days, all right? So when the number of days increases by 1, the predicted tumor volume, that's my y variable. Since the slope is positive, I'm going to pick increases by 37.25. And I think it's like millimeters or something. Cubed. All right, so that is how you interpret the slope. Let me take a pause. Any questions on that? Okay, so that's one of the big things from this lesson, okay, is how to interpret slope. So make sure you guys are feeling comfortable with that. Interpreting the correlation coefficient. So again, use Duff's, right? So there is a, let me use a different color. So I would say there is a positive, strong, linear relationship between number of days and tumor volume. All right, and that is how I would interpret the correlation coefficient of 0.998. Okay, let's go on to our y-intercept if there's no questions. Okay. All right. So the y-intercept, if I were to interpret the y-intercept, I would say something like, sorry, let me clear this out. When number of days, my x variable is 0, right? When number of days, my x variable is 0, the predicted y is negative 269.75. Okay, so let me do the same thing I did for the slope. So to interpret the y-intercept, I would say when your x variable is 0, the predicted y variable is, and whatever your y-intercept value is. All right, so that would be my interpretation of the y-intercept. In this case, it doesn't make a lot of sense, right? You can't have a negative tumor size. That's like, I'm trying to imagine what that would be. That would be like having like a hole instead of a tumor. Like, I don't know what that would mean. So in this context, the y-intercept does not have any meaning because it's negative and you can't have a negative size tumor. Just doesn't make sense. All right, so then we won't go ahead and interpret that since there is no meaning on that one. All right, next one, number 5. Predict the average volume of the tumor for 20 days after injection. Okay, so this is the whole point of having your least squares regression line, is so that we can predict. So in order to predict, we're gonna plug in 20 for days. All right, so literally just plug it in, calculate it, and there you go, 475.25. Right. So that's the whole point of this LSRL, right, is to be able to make predictions. All right, I did that one, you guys do the next one. So predict the average volume for the tumor for 5 days after injection. All right, go ahead and do it, and then I'll call on somebody, see what you got. All right, and let me go to Billy. Billy, what did you get for the tumor size?
Wouldn't you just say, can you hear me?
Yes.
Wouldn't you just say 0 because you can't have a negative volume?
True. What was the negative number though, just in case?
Oh, I didn't actually look for it because.
Oh, okay. Go ahead and quickly calculate that. Yeah, but you're right. It does end up being negative.
Negative 83.5.
Perfect. Nice. All right. So you get a negative number and you're absolutely right. This makes no sense. Now, the reason why this line kind of, in a sense, failed to predict at 5 is what's known as the danger of extrapolation. The danger of extrapolation. And why this is an example of that is because if you look at our data, our X values range from 11 to 27. 11 to 27. Our prediction, or what we're using to predict of 5 days, is outside of the data range, right? It's below 11. So that's what extrapolation is. It's when you're trying to make predictions for the Y values outside the range of your data. And that's what you don't want. All right, that's what extrapolation is. So for example, okay, this is a very obvious example of extrapolation, okay? So men's age at first marriage, okay? Back in the early 1900s, right? It was starting to go down. So it's like 26, you know, a little lower, 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 lower. If we were to make a best fit line with just the blue dots, it would predict that you guys, all right, men in this class, you guys would be getting married at like, well, like when you're babies, okay? You'd be getting married at like 1 if we continued using this line for prediction. Clearly, that trend did not continue. So we would not want to use this line to predict outside of those blue dots, the years in the blue dots, okay? So that's extrapolation. Very dangerous, very dangerous. And the further away you get from the data range, the more dangerous it is. All right, any questions about extrapolation? Ooh, all right, we got 2 minutes. So last thing I want to show you guys is what's called Minitab. And this is a statistical software package that I actually used when I was in college. We were using Minitab. And I just want you guys to be able to read it and be able to find the least squares regression line. So I'll let you guys know that this up here, predicted volume is equal to, you know, all that. That's our least squares regression line. This is not always given in Minitab. For some reason, it just doesn't always give you this. But they do give you the stuff below. So just know that this number right here will always be the y-intercept. All right. The word constant will always be there. And the number right next to it, right next to the word constant, is always the y-intercept. And the number right below it will be your slope. Okay, so just be able to pull out those two numbers and know what those two numbers mean. Okay, so y-intercept, slope. All right, and this stuff we'll discuss in chapter 13, so you don't have to worry about it for now. Okay. All right, good job, guys. Questions?